Okay, so now I'm going to tell you about how to find the formulas of the combinations of normal ions, polyatomic ions, and transition metal ions. Normal ones are pretty easy. The goal of any particular formula, the idea, is that you cancel out all the charges so that the compound ends up neutral. The way that you do that can vary. So I'll show you two ways to do a normal one. Let's say I want to know what this looks like. Sodium ions and chloride ions. I want to combine sodium and chlorine and see what happens. So one way you can do it is to draw the Lewis dots. I got sodium with 1 dot. I got chlorine, and it has 7 because this is where chlorine is. It's got 1, 2, 3, 4, 5, 6, 7. What's going to happen when you stick these two together is chlorine needs 1 to get 8, so it'll eat this. Sodium needs to lose 1 to reveal its inner 8, so it loses this one so it can reveal its inner 8, like that. What ends up happening is that you get a sodium, like this, it's positive 1, lost its electron, and you have a chlorine like this, 1, 2, 3, 4, 5, 6, 7, 8, that gained an electron, so it's negative 1. Once you know how many sodiums and chlorines were involved in this interaction, you just tell me. You say, okay, well I had sodium and I had chlorine. I had 1 sodium and 1 chlorine, but chemists are kind of lazy and they don't like to write ones, so we won't. NaCl. The problem with this is when you have longer, more annoying connections. Like, for example, if I have this. I have Ca and N. I want to know what calcium and nitrogen make together. So calcium will have 2 valence, because it's right here, and 1, 2. Nitrogen will have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And the nitrogen will need a lot. It'll need 2 from this calcium, but it needs another one, right? So another calcium comes over with 2. Gives 1 here, but now this calcium needs to be finished, right? So another nitrogen comes up, 1, 2, 3, 4, 5. So this one goes here, but this nitrogen is not done, right? It needs 8. So another calcium comes up, 1, 2. This one goes here, this one goes here. And then now, after all this, we're done. This is a pain, so we don't do it. We do an easier way. We do a shortcut way to figure out how to make everybody neutrally charged, how to make the combination neutrally charged, so we give up as many ions or electrons as somebody else is taking. And that way we call the swap and drop. This works for every single one of these, for normal, polyatomic, and transition. It makes it so we don't have to think in order to figure out a combination that'll balance out the number of electrons being given and received. The way the swap drop works is you take the ions with the charge. So like I have X and it has a positive, I don't know. You have Y, it's got a negative, I don't know. And then what's going to happen is you swap the numbers and drop them down. So that goes here, this goes here. And maybe I'll make this not both question marks. This one will be positive question mark. This will be minus square, just to make it different, right? So you swap and drop, and what happens is the formula looks like this. You have X, and then whatever number was originally on the Y goes here. Y, and then whatever number was originally on the X goes here. That's what happens for the swap drop. And if these two need to be divided to get to the same number, like if this is a 2 and this is a 2, for example, you're going to cancel it out to make it the simplest possible version to be a 1 and a 1, which you don't write down. That is hopefully not too complicated. I'll show you some examples. So let's say that for normal ones, I want to do these. Okay, I want to do lithium and fluorine, see what happens when I put them together. To do the swap drop, I say Li is the first one. Here it is. Now this column is positive 1. If you don't remember why, watch that video. Fluorine is right here, F. The ion it makes will be minus 1. So to figure out what the formula will be, I swap the numbers and I drop them down. So this goes here. This number goes here, and I say Li1, F1, but chemists are lazy, they don't write ones, LiF. That is the formula that you get for the combination of lithium and fluorine. Sr and N, well, strontium is right here. It's going to be in the positive 2 column. Sr will make a positive 2 ion. Nitrogen is right here. This is in the 0, negative 1, negative 2, negative 3 column, so nitrogen is negative 3. This number will go here, that one will go there. We drop any positives and negatives. So we get Sr3 and 2. That is what you get when you combine strontium and nitrogen. Finally, last one, Al and O. Well, aluminum is right here. It's in the 3 plus column. Oxygen is right here. It's in the 2 minus. So Al, 3 plus, O, 2 minus. Take the numbers, swap and drop them down. Probably should have been doing this in different colors. So we get Al has the 2 that was originally on this oxygen. And the oxygen has the 3 that was originally on aluminum. So O3. This is what you get when you combine aluminum and oxygen. Easy enough for normal ones. What about polyatomic ions? So here are 3 combinations that involve polyatomic ions. What you want to do in order to figure out the swap drop is you write down the first one, okay, potassium. It's right here. So it's positive 1. PO4, well, to figure that out, I really got to look it up on my polyatomic ions chart right here. So PO4 is down here. It's called phosphate, and it's 3 minus. So I'm going to say PO4 and 3 minus. I just put parentheses around it to remind me that this is not 5 different things, like 1P and 4 O's. It's one big blob. So I do the swap drop. This number goes here. This number goes here. And what I get is that K and PO4 combine to make K3, because that was originally here. This is 3 minus. So K3, PO4. And sometimes you'll see it like this. Oftentimes you will see it with the parentheses to remind you that PO4 is not 5 different objects. It's one big blob. Mg and OH. Well, Mg is going to be 2 plus, based on where it is on the table. It's right here. Mg. It's in the 2 plus column. OH, well, you got to look it up. OH is right here. It is called hydroxide, and it is -1, because if there's no number there, there's a 1, because chemists are lazy. OH, -1. So take that, drop it down, take that, drop it down. And this Mg gets the -1 that was originally on here, but we dropped the minus, so it'd just be 1. And we also dropped the 1, because we're chemists and we're lazy, so we don't draw it. Now, Mg is 2 plus. So the number that is on the OH at the end is going to be a 2. So OH and a 2 outside of the parentheses. We have 2 hydroxides. So MgOH2 is how you draw the formula for that. Finally, if you have more than one polyatomic ion, it's not more difficult. I have NH4, which is +1. And then I have ClO3. So maybe I should have looked it up here. NH4 is right here. It's ammonium. It's +1. ClO3 is right here. It's called chlorate, and it is -2. So I swap the numbers and I drop them down. That means that the NH4, NH4, 4, this 2 is going to go down here. So I write a 2. Now maybe this is confusing to you because I have a 2 and a 4 on opposite sides of these parentheses right here. But what this means is that I basically have 2 4-headed monsters. Ammonia looks like this. This basically, it's a nitrogen glued to a bunch of hydrogens. They're stuck together. So they don't get separated. It's like a 4-headed monster, right? So I have 2 4-headed monsters is what this means when I have 2 ammoniums. Anyway, this one is going to go down here on the ClO3. So ClO3, and I have 1 of them, but chemists don't write 1s. We're lazy. So NH4, 2 of them, and then ClO3, which sometimes you will see it without the parentheses, but I like to write it with them before you really know what you're doing. Like you probably don't. So that's how you swap drop with polyatomics. Finally, swap drops with transitions. Okay, so the transition metals are normally in here, the D block. Sometimes they go in here, like lead is one of them, but these are the transition metals. They don't really fall under the normal categories. They're all weird because they're all different versions of them. But it is not more difficult because when I'm talking about a transition metal, I have to tell you which one. You never have to figure it out. So for example, here's some transition metal combinations I can make. So lead 4 and fluorine, copper 2 and nitrogen. Now this fluorine is easy. Fluorine's here. It's -1. -1. But lead is more annoying because there are several different versions of lead, right? This is lead. And I just kind of highlighted it. It is in this transition block, even though it's not there. Maybe iron would have been better, but whatever. So you have lead 1, you have lead 2, you have lead 3, and you have lead 4. There are several different kids in the lead family. There's not just one. So when I say that lead kid, you don't know who I'm talking about. But if I tell you the 4th lead kid, you do. You know it's this one. So once you know which particular version of the transition metal you're talking about, you write it down. Pb 4 plus, that's what I have. So Pb 4 plus, and then fluorine is -1. So what you do is you swap the numbers, drop them down. So swap, drop, and you end up with Pb 1, but we don't write 1s because we're lazy. F4. This is the combination of lead 4 and fluorine. Copper 2 and nitrogen. Well, you have a couple different versions of copper. You have this version. Maybe I should have started with a 1. Okay, so you have this. You have this, you have that, and you have that. Several different versions, several different kids in the copper family. But that 2 lets you know that it's this. Copper 2 is the version you're dealing with. So you have copper 2, that is the copper kid you're dealing with, and nitrogen, which is 3 minus. So once you have the charges, you just swap, drop, like that, 2 and 3. So you have 3 of the coppers, 3 copper 2s, and you have 2 nitrogens. Nitrides. So when I say copper 2, it does not mean there's 2 of them. It means that it is the 2 plus version of copper that I have. So this right here is the combination of copper 2 and nitrogen. Hope that was helpful. I'm sorry, I forgot one really important thing. So if when you do the swap drop, you get the same number or a number with a common divisor for both of them, you got to do something special. So let's say that you want to do this. You have calcium and then you have oxygen. You want to combine them and see what you get. So you look up and you say, okay, calcium is 2 plus and oxygen is 2 minus. So you say Ca2 plus, O 2 minus. You swap the numbers and you drop them down, like that one goes here, that one goes here. What you get is Ca2O2. You can write this down and you will not be right. This is not correct. The reason why it's not correct is because these formulas don't actually tell you how many atoms you have total. They tell you the ratio of the atoms in a crystal. So for example, if I have this, sodium chloride, that means that I add 1 sodium to the crystal, and then I add 1 chlorine to the crystal. And then I add 1 sodium to the crystal, and then I add 1 chlorine to the crystal. The ratio is 1 to 1. So then I add 1 sodium to the crystal, and I add 1 chlorine to the crystal. So like the ratio that I'm building this with is 1 to 1, which is why I say Na1Cl1. But because these formulas actually just tell you ratios, the ratio of 1 to 1 is the same as the ratio of 2 to 2, is the same as 3 to 3. They're all the same. So if you end up with the same number on both of them, you have to simplify it to the simplest ratio. So Na1Cl1, that's easy. But if you end up with something like this, if you end up with Ca2O2 after you swap and drop, you're not done, because you can simplify this. 2 to 2 is the same thing as 1 to 1, or 1 to 1. What am I talking about? 1 to 1. So you end up with CaO. That is the formula for calcium and oxygen. Similarly, if they don't have to be divisible by the same number, I mean, they don't have to be like both the same number. You can end up with something like this, right? Let's say you do a swap and drop and you want to know what the formula for iron 4 and sulfur is. So you say iron. Well, I got different versions of iron. I have the +1, and then I have the +2, and then I have the +3, and then I have the +4, because everybody in this neighborhood down here, the transition neighborhood, these all have a million kids, right? So when I tell you iron, I have to tell you which specific iron I'm talking about. I'm talking about iron 4, the 4th iron kid. But for sulfur, well, sulfur's right here. There's only one version of sulfur, 2 minus. So I end up with Fe4 plus and sulfur. I don't have to write the Roman numerals for sulfur because it would be weird to say like, yay, bring me the first Smith kid. There's only one Smith kid. What do you mean the first one? Anyway, so I have Fe plus 4, S2 minus. The transitions are always going to be positive. Forgot to mention that. This goes there. That goes there. So I get Fe2, S4. But just like before, right, you can simplify this. Because 2 to 4, you can simplify that. It's the same as 1/2. So you will write down Fe2S4 when you do swap drop, but you divide them both by 2, because you can do that. You get Fe1S2, and the 1 goes away. So this is the combination of iron 4 and sulfur. That's how you do the formulas. Hope that was helpful.